Okay, it's a great pleasure to have Patrick Wensing. Patrick is an assistant professor in the Department of Aerospace and Mechanical Engineering at the University of Notre Dame, where he directs the Rome lab. He received his PhD in electrical and computer engineering from the Ohio State University and completed his postdoc on control system design for the MIT Cheetah's robot. Patrick does research on dynamics, optimization, control of legged robots, and assistive devices. With this, we are looking forward to your talk, Patrick.
Excellent. Thank you, Majid. And thank you to all the organizers for the invitation to be a part of this impressive program. So today I'll be telling you a little bit about tailoring model complexity in MPC and some different formulations of MPC that we've been kicking around in my group. As Majid said, I'm at the University of Notre Dame, where I direct the activities of this the Robotics Optimization and Assistive Mobility Lab, or ROAM Lab. And just to give you kind of an overall flavor of what I've been working on these days, we're in my group, we're looking to advance mobility, both for legged systems broadly defined, quadruped and humanoid robots, as well as legged systems that we might wear on our bodies in the form of lower limb exoskeletons or lower limb prostheses. So, on the left here, our goal is to be able to send legged robots anywhere on Earth, whereas on the right, we'd like people to continue to be able to go anywhere on land, I should say, even after they've had an injury that might limit their mobility. So I'll mostly be focusing kind of on this this left-hand side, but we're really interested in looking at how we can translate some of these model predictive strategies and the control designs that we're looking at over to these other high impact applications. So in terms of MPC, I think it's been a really exciting time over the past number of years. So this video is a few years old at this point, but here's a video of Cheetah 3 using MPC to climb stairs. And so kind of, what's under the hood here is that you've got a model predictive controller that's thinking about how to move the body through space, optimizing forces under the feet to do so. You've got some heuristics that are layered in there to help swing the legs into position. And we can tune that up quite well for these types of scenarios. However, I think as we start to think about sending robots out into the real world, inevitably they're going to come across scenarios that are unlike ones that they've seen in the lab. Whether we're sending a robot to support our troops, into a disaster zone, to the scene of a fire, or into our homes, our robots are going to come across environments or scenarios that they've never seen before. So if we think about contrasting MPC and learning, our robots are inevitably going to be kind of operating out of distribution in many cases in the real world. And so I'm very motivated in terms of continuing to advance MPC as kind of a core component. I think a fundamental need for our systems is an ability to kind of predict through the consequences of their actions so that they can creatively devise solutions when they find themselves in these new regimes. So what I'd like to do here kind of to open is to reflect on the structure of prediction that we've been conventionally pursuing within legged locomotion. And then I'd like to make a case for how I think we should be perhaps approaching it instead. So conventional MPC and legged locomotion is pursued often via hierarchy of optimization problems, right? With the standard thing being to adopt some simple model and think about how it evolves over the long term. So for instance, in that video at the beginning with the cheetah, it's using a single rigid body model that many people have had great success with, and optimizing forces under the feet in order to propel that body where it needs to go. So you can think when you get this right, you figured out how to move the body, but there's still a lot of details that are left in terms of swinging the legs and the like. So you got this low dimensional plan that you need to turn into a whole body plan. So the conventional thing to do is then to try to match that plan with a shorter term controller. And here I'm showing you like an MPC problem posed over some short horizon that we might think of for the whole body model. But you can think as this time horizon goes down to 0, we degenerate down to more of the conventional optimization-based QP controllers, whether those are operational space QPs or CLF QPs, or et cetera. A further simplification that's often made, right, would be to use just like a J transpose F, which works quite well in many cases for the cheetah. Although Donghyun Kim, for instance, has shown some benefits of these operational space methods at higher speeds. This works in stance and in swing. As I said, there's some heuristics that are included to figure out where the foot should go and what trajectory to follow, and a heuristic swing leg controller. And so kind of my overall view here is that we can get this working for specific scenarios, but as you go out into the more general real world, maybe these simple models are limiting, and maybe you need to pick a different simple model, or maybe go all the way to the whole body case at this top level. And I'd like to kind of think through some of those trade-offs that we usually think as being there. So kind of on one side of the spectrum, you can think in terms of your long-term planning, we might adopt a simplified template model like the lip or the slip. And we do this to manage complexity because we can compute these fast. But it comes at a price, right? These models are restricted in the motions that they can create. When you follow a slip model, your center of mass has to follow this spring dynamic, and that places some restrictions on the motion that you can create. Of course, we can kind of move across the spectrum here, increasing details, considering a single rigid body model adds orientation, or which has been quite popular, looking at centroidal dynamics plus full body kinematics, or kind of all the way on the other end of the spectrum is to plan considering your whole body dynamics model. And I see the benefit here all the way on the right really is that you're unlocking the full performance envelope of the system. There are some push disturbances where if you act like a spring, you're not going to be able to reject them, whereas here you can do anything that the system is capable of. And of course, this comes at a price of slower computation. I'd say, earlier this week, actually, I was in a workshop for the American Control Conference, and everyone was saying that, you just can't do this real time. And, I think that many of the people that are on the call here know that that's kind of not true. And we could do a better job of communicating that to the control community more broadly. For me, I'm very motivated, and I was originally motivated by some of the work by Imo Todorov and Yuval Tassa almost 10 years ago now, where they looked at whole body MPC in their early days of Mujoko. And I think here, if you look at these motions, they're incredibly creative, and this is all just coming through gradient descent, and I think that's just really exciting. And of course here I've noted that this is 7 times slower than real time, which is a barrier. And there's been some really phenomenal progress, since these original results, from the teams at LOS and ETH that have served as a lot of inspiration for us. And so we've been looking to contribute to this push and help enable us to demonstrate continually more dynamic behaviors on these robots. So I guess before we leave here, I'd like to note that often we think of picking one template model or one model on this spectrum, and we think there being this kind of unavoidable trade-off that either I'm going to pick the simplified model and I'm going to be able to compute quickly with it, or I'm going to go with more details and it's going to be slower. And we view that trade-off as unavoidable. I'd like to challenge the notion that that trade-off is unavoidable, and I'd like to do it through a simple example here. So let's consider this hiker trying to cross this stream, and imagine the hiker needs to go from where he's at to over on the right. And I'd like you to put yourself in the hiker's shoes and think, what might you be thinking about in your plan for getting across this stream? I'd guess that probably, in the near term, you might have some idea of how you're going to move your whole body, but as you think about your plan further out into the future, there's going to be a little bit more fuzziness or abstraction to it. Maybe for the next step, you have an idea of which rock you're going to step on, but then further out, you probably just have a really rough plan in mind. And so at a high level, I think that we should be focusing our MPC and structuring our MPC more like the hiker does his prediction here, right? When we're doing MPC, we're constantly reevaluating the plan, so it doesn't make sense to be using our whole configuration detail all the way out over our prediction horizon. So to kind of contrast what this hiker is doing versus what we're currently doing, a little bit more formally, in conventional MPC approaches for locomotion, we solve a hierarchy of optimization problems. We come up with some plan with our simple model, and then we try to track it in with our whole body model over a shorter time horizon. And this puts a lot of kind of stress on this simple model to be able to do the right things for us. And again, here, this is a hierarchy of optimization problems. By contrast, I think we should be pursuing kind of one problem posed over a hierarchy of models. That's to say that just like at the hiker, when we're thinking about our prediction horizon in the short term, we should be thinking kind of in full detail. But as we start predicting further out, it's probably okay to incorporate those simple models here. And I think by doing our planning in this way, there's a lot less, a lot less demand on this simple model because you're never trying to exactly track it. I should note that we published this idea somewhat recently in REL, and actually around the same time in 2021, there was a paper in IEEE Transactions on Control Systems Technology by Chris Gerdes and his team at Stanford, where they were looking at similar structured predictions for their high performance driving applications, where they would use a full car model in the near term and a double integrator model in the long term. And I think it's very much similar in spirit. We've seen Steve Tonneau kicking around some similar ideas developed independently. And so I think there's a lot of momentum going in this direction. Okay, so in terms of how I'm going to structure the rest of my talk, I'll tell you about some of the results from this model hierarchy predictive control idea. We'll look at it for both a quadruped and a biped. This is some work done by my graduate student, He Li, and an undergraduate student, Robbie Fry. Robbie's great. He's looking for PhD opportunities for next year. So if you're looking for someone, I'd be happy to connect you. Then I'll go into some more kind of nitty-gritty details about solving these trajectory optimization problems and some advances that we've been considering there by my students, He Li and John Nana. And then, this is going to be very model-based, and I figured I should say something about learning. And so at the end, I'd like to, make some comments about kind of choosing what to learn and where to include it in the framework. And I'll tell you about some initial ideas that we worked on there with Octavio Villarreal, Dr. Villarreal from IIT when he was visiting my lab. Okay, so let me jump into this first part on the main idea of the talk. So I'd first like to make an observation that these model hierarchies that I've discussed are really just instances of hybrid systems. So usually in locomotion, we think about dividing our gait up into these different phases. So maybe we have a flight phase here, and then there's an instant when the foot touches the ground that you have some impact that we might encode in a reset map. And the high level observation that I'd like to make is that when we think about this reset map, it's just mapping a state before the event to a state after the event. And it doesn't necessarily need to be for the same model. So we can incorporate into a reset map like this also a transition between models. So here the red represents flight dynamics for the full model. The green represents stance dynamics for the simplified model. And so as long as we can solve optimal control problems posed over general hybrid systems models, then we can instantiate this model hierarchy predictive control idea. And so I'd like to take that we can solve these types of problems as a given here for a little bit and just focus on the results of the framework. And we'll come back to how we solve these problems in a little bit. So to kind of start getting you on board with this idea, let's consider comparing it to the simple model MPC for some push disturbances. So here I'm going to take and I'm going to push on the quadruped for 100 newtons with 100 newtons of force for 30 milliseconds during flight. And here are the results for using the planning strategy I discussed at the beginning, using that simplified model. So here, there's this push disturbance, and then in the subsequent stance, the knee hits the ground. There's this whole body detail that wasn't thought about during the planning that leads to a failure in this case. By contrast, if we plan more like the hiker, thinking about the whole body detail over a couple of gait phases into the future, and then thinking more abstractly out for the rest of our plan, in that case, we succeed from this push. This is one case, so I don't expect you to be convinced. But we did take this one case and extend it to a broad range of pushes, doing some simulation experiments. So here on this graph, on this x-axis, I'm showing the magnitude of some push disturbances that were applied from 0 to 160 newtons. And on this y-axis, I'm showing you the probability of success. And so this tube here, this middle line, represents empirically for our Monte Carlo trial what percentage of time we succeeded following these pushes. And this tube represents a 95% confidence interval for the analysis. So here, at first, I've drawn the simple model MPC. I've planned 0 gait modes using my full body model, 8 gait modes using my simplified model, and we start to break down around 30 newtons of push disturbance. As our high performer, we've got our whole body MPC using the full model for 8 gait modes. And that one doesn't start to break down until 130 newtons of push. So let's see what happens when we switch up how we do this, consider this horizon. So conventional result from MPC is that you shorten the horizon, you kind of don't make as good of decisions because you're being myopic. And so we see that here you break down earlier around 100 newtons. And what we're going to do is we're going to take this horizon and add prediction with the simple model on top of it at the end. And so if we do that, I think 4 gait modes with our whole body configuration detail, 4 gait modes with our simplified model, it helps us to make better decisions, as shown here in the purple. And you can think as you take this transition point, if you were to slide it over and do more whole body planning, you should do better, you would think, and we see that in some cases. But surprisingly, it's not, that performance is not uniform in that regard. So if we just plan for 2 gait phases with our full body model and 6 gait phases for our simplified model, we get this, this red curve, which performs comparably to the whole body MPC for these largest push disturbances. That's to say, in terms of the hiker, getting the most benefit or most bang for your buck, you really only need to plan with the whole body for just a little bit into the future. And I have some conjectures as to why that might be the case that perhaps we can discuss at the end. The benefit here really is that this red one is much faster to compute. So on this graph on the right, I'm showing you the solve time that was required each time we ran the optimization. And I'm normalizing everything to the whole body MPC case. Right? So the whole body MPC takes the most computation. Down here, simplest computation is the simplified model. It's fast, but you don't get as much push robustness. Here, the second best time-wise is this this hierarchy where you just think for a little bit of time into the future using your whole body detail. So MPC significantly lowers the computation time, kind of with minimal performance hit. All right. So this worked for a quadruped. What about other systems? Or I guess I'm not done with the quadruped yet. That's right. Sorry. Let's take a look here at a problem of jumping over a gap. So this was a result of solving MPC in simulation. And so here I'm drawing the red piece is the whole body plan, and the blue piece is the simplified model plan. And so you can see kind of the main idea is that when you're doing this, this type of prediction, you're never executing the simplified model part of the trajectory. You're always staying on that portion where you have a whole body plan. The benefit of doing of structuring the prediction in this way can be also seen from a standpoint of if you have a limited computational budget, the model hierarchy allows you to think further out into the future. So we took 2 configurations that required the same computation time. 6 gate whole body MPC here shown in red, the model hierarchy shown in blue. These 2 require the same amount of computational effort. And with this blue one, basically it allows the robot to see the gap earlier and make proactive decisions earlier in its gait cycle to do a better job of tracking the desired speed. We've been making some progress toward getting this in hardware. Here's some initial tests with the mini cheetah that we have down in the lab. Mini cheetah is really phenomenal. I can't thank Songbei enough for giving this to us on semi-permanent loan. Here I would emphasize that the planning is not in an MPC fashion online. We've computed a trajectory offline, and we're just using kind of the gains that you get out from DDP for our online tracking. So as we start to move toward online MPC, I would expect the performance to just improve further. Okay. We've been looking at this for other systems as well. So we looked at it for a biped model, and I'd encourage you to take a look in the paper for more details there. It's pretty much the same conclusions, just that for a biped model, the balance is a little bit trickier. So you need a little bit more whole body planning in that case. We've also looked at this for a quadrotor. So here's in this example, we've got this quadrotor starting over here on the left. It needs to fly to this spot on the right, and it's got this obstacle field that it needs to fly through. And so I've got these two prediction horizons here. One uses the full model for 1 second, and then the simple model for 0.1 second. And then over on the right, this one uses less full quadrotor planning and more simple quadrotor planning, where we just treat it as a point mass. And so on the left, since you're accounting for the full dynamics, you can't plan as far out into the future, and that leads the quadrotor to take a bad path through this obstacle field. Whereas on the right, by thinking more like the hiker, we can make better use of our computational resources, and the quadrotor is able to kind of proactively navigate around those obstacles. The benefit being that by thinking further out, you can be more proactive, whereas on the left, you have to be more reactive, and that often takes large control efforts. So to wrap up this first part, I think this picture of the hiker is the main takeaway that I hope you'll have. Planning with a hierarchy of models enables prediction further into the future, and considering a limited compute budget, this strategy leads to higher performance than whole body or simple model MPC alone by combining them together. As I said, I think this idea is applicable for many systems and in many configurations, and I'd love to see more folks trying it out in yet other configurations. I will note that we have a good ways to go for computing at online rates, but we've got some phenomenal tools from the community to hopefully help us draw on to achieve that. And the final caveat I'd like to make here is just that at the beginning, I motivated the need to move away from heuristics. And here we've kind of put the heuristics a little bit in a different spot, that our choices of simple models are essentially heuristics. And there's some great work by Michael Posa, for instance, that's looking at how we can formalize this model choice and that we're tracking quite closely. So, okay, let me take just a quick second break here. Okay, so I hope I've got you on board with the way that we are looking at structuring this prediction. Let me tell you about how we're actually solving these problems and how we're looking to solve them faster. So we've been using DDP, like many folks have, and I know that probably many of you on here are familiar with this, but for those of you that aren't, I figured to give a brief intro. So differential dynamic programming, or DDP, solves a discrete time optimal control problem. There are some nice continuous analogs of this. But to solve this problem, we often might try to do so by constructing the value function, or optimal cost to go, which we know satisfies Bellman's equation. And if we could solve this, it would be great. We'd be very happy people, but we can't because it's a little bit too complicated. And so the idea is that instead of trying to solve Bellman's equation everywhere, what DDP does is it takes your an initial trajectory and kind of looks nearby around it, considering some small state and control perturbations. And so if I take this equation and I expand and do a Taylor expansion to second order on the right-hand side, I can find how I should change my control based on how far my state has deviated from this initial trajectory. And I'll highlight that this kind of feed forward and feedback component both depend on an approximation of the Hessian and gradient of this optimal cost to go at the next time step. The nifty thing with DDP is that we can take this answer and plug it back into that equation, and it gives us a difference equation that relates the Hessian and the gradient at one time step to the Hessian and the gradient of that value function at the previous time step. At a high level though, what this strategy allows us to do is to perturb our state and control trajectory to decrease the cost, and then we can repeat it until we get something optimal. So DDP in its most kind of basic form is for a normal vanilla discrete time system. We'd like to extend it to hybrid systems. And so what we've done is to extend it, let's consider the same cost structure as before, but we're now going to sum up over modes indexed by I. So we've got these costs over different modes. We've got different dynamics in each mode. I've written these as continuous dynamics because you can think that this discrete time system really might represent some sort of integration scheme applied to your continuous dynamics. You got this for each mode, and then you've got a map that potentially transitions between your different modes, incorporating impacts or potentially a model transition in the model hierarchy case. DDP also kind of just works with dynamics constraints. We're interested in incorporating switching constraints as well as other inequality constraints. And so I'd like to tell you a little bit about how we've looked at solving this, kind of working from the in and moving our way out. So this middle problem can be solved via DDP. When we incorporate this reset map, we've got a small extension to it that we call impact-aware DDP. And then finally, we've been looking at augmented Lagrangian and reduced barrier strategies that are inspired by some of the work of the co-organizers to help complete the picture here for the outer part for hybrid systems DDP. So in terms of this impact-aware step, we've got some dynamics, we got our reset map, and then some other dynamics on the other side of it. And during each of these yellow segments, you can just apply conventional strategies to relate the value function at one time step to the value function approximation at a previous time step. So really the only trick here is how do we account for this reset map? Well, we can write down the cost to go before this reset and relate it to the cost to go after the reset. And through just some second order calculus, expanding this out, you can get a difference equation that relates Hessian and gradient post-impact to Hessian and gradient pre-impact, where this matrix J is just a Jacobian of your reset map. The thing I'd like to highlight here that's a little bit subtle is that we're solving this problem where mode sequences are fixed and implicitly mode timing is fixed. So usually when we think about these resets, you might have additional terms that account for how perturbations in states affect perturbations in the switching times. Whereas in our case, we account for those with the outer layers of our framework. So like I said, we haven't yet addressed making sure that the foot is essentially on the ground when we carry out these impacts. So more generally, how can we handle constraints in DDP? One strategy is to consider adding penalties for your constraint violations into the cost. And this can often work well. If you're not happy with your solution, you increase this penalty term that shows up in your cost function and you resolve. However, this type of a problem can become ill-conditioned as this penalty parameter becomes large, and this has motivated others in the community Ryan Russell at UT and Zach Manchester and some other folks at Stanford and CMU to consider augmented Lagrangian strategies for handling these equality constraints. And the main idea there is again to convert a constrained problem into an unconstrained one. But now we're going to add this additional Lagrange multiplier term, and with lambda considered as a Lagrange multiplier. And from iteration to iteration, if we're not happy with the solution, we're not just going to update the penalty parameter, but also this Lagrange multiplier. And kind of overall, the nice thing is that your constraints here can be satisfied with a smaller value of this penalty parameter, which helps with numerical conditioning. So in terms of how this works out for us, on this graph, I'm showing the solution of a bounding optimal control problem for the robot. And on this graph, I'm showing the evolution of the algorithm. On this x-axis is the number of iterations. On the y on the left is the evolution of the cost. And the y on the right is, in red, is the evolution of the constraint. So here we see we keep our Lagrange multipliers constant. Then once we change them, it allows us to get more improvement in terms of our constraint satisfaction, change them again, and our constraints really zero in. The thing that I'd like to emphasize with this is that until the end, you almost kind of don't have a a hybrid feasible trajectory. That at the beginning you're switching anytime, even if the foot isn't on the ground, and acting like it's on the ground. And even after we incorporate our impact aware DDP that accounts for those impact impulses that you would see, those impulses are happening, and being modeled as happening at a location that's not the ground level. And so it's only through incorporating these augmented Lagrangian strategies that you get a hybrid feasible trajectory in the end. And I think there's some pros and cons associated with that I'd be happy to talk about with you all a little bit later. I think I'm gonna, based on where I'm at on time, I'll ignore this part for now, but just to say that we have a strategy for accounting for changing the switching times in the framework, and that has some improvement relative to previous strategies that have been shown in the literature and adopted by others. And I think there's still a ways to go there. And again, that's something that would be potentially great to add in the discussion. For all these strategies, the main computation cost associated with them is getting that gradient information and Hessian information, and it really boils down to a problem of calculating derivatives. And so what I'd like to do is to kind of go into that difference equation, into some of its details, to motivate why that's the case, and explain something that we've done to help accelerate this process. So I brought back that difference equation that relates the gradient and the Hessian of the value function at one time step to that at the previous time step. And so here I'm using the prime to denote essentially one time step later. If I were to kind of open this up and to show you some of the details don't matter so much. We're going to define all these temporary quantities and then get our value function update as follows. I don't want to go into the details of these, but I wanted to take a look at the structure here. So these terms in blue, if we look, we've got some gradients of our cost, Hessians of our cost, got a gradient of or a Jacobian of my dynamics, and this known quantity from the next time step. So to compute all these terms in blue, I need the first order dynamics or derivatives of my dynamics. And there are some really phenomenal algorithms that are available out there, for instance, in the Pinocchio package. Now, in terms of these other terms here, these address second order dynamics effects, and they're often ignored in ILQR. And this does come at some expense. So if we compare how ILQR in blue converges versus DDP in red, when you're close by an optimal solution, DDP has this nice quadratic convergence property that we're losing out on by dropping these red terms. And the real culprit here is that these terms in yellow are 3D tensors. They're Hessian tensors for the dynamics. And there's ON cubed terms here. So computing them in the past is almost strictly more complicated by an order of magnitude compared to the ILQR terms. So recently we found a way to compute these terms in red with the same computational complexity as the terms in blue. I'm pretty excited about the idea. So to illustrate why we can do it, let's think first about how derivatives can be efficiently computed in practice for complicated function evaluations. So let's just consider some function h of x that maps from Rn to R. You might think of this as just a neural network, for instance, right? The nice thing with neural networks is no matter how complicated the network is, we can still train them efficiently due to the celebrated backprop algorithm. And the nice thing is that with backprop, you can get the gradient of this function with the same complexity as computing the function itself. If this weren't true, we would be totally hopeless in terms of tuning our neural networks. And it's really a phenomenal result. So let's see how we can apply that in our case. So our goal is that we want this vector dotted with this Hessian tensor of second order derivatives. What I'm going to do is I'm going to define lambda as this vector that we have known coming in, and define a scalar function of lots of variables as follows. It's this vector lambda dotted with my dynamics. So if I go back to my neural network example, this really is kind of the same thing. I've got a scalar function of lots of variables. I can evaluate it by taking this vector lambda and dotting it with my dynamics. And we know that dynamics can be computed with complexity ON. So as a result, using our backprop trick or reverse mode accumulation, we can calculate this kind of first order term, lambda dotted with this Jacobian of the dynamics, in the same exact complexity as computing this function h itself. So ON. Right? Once we have that, we can apply kind of pick your poison auto diff to that, and we can get this desired result with complexity ON squared. So in fact, before we thought that the DDP was going to be ON cubed to do it, you can actually do it in ON squared by relying on this trick. One thing that we've seen previously in the literature, though, is that often the dynamics, we can view them in kind of one of two ways, and it's more efficient to use one way than another. So we have our our inverse dynamics, which we can evaluate with recursive Newton-Euler in time ON. And we also have our forward dynamics they're closely related to one another that we can evaluate with the articulated body algorithm in ON time. But this second strategy is much more complicated than the first one. So some nice insights that have showed up previously in the literature and that are implemented in Pinocchio is to exploit this first order relationship between the partials of inverse dynamics and the partials of forward dynamics. And so in fact, you can generalize this to the second order case. I'm going to give you just kind of the high level idea of why we can do it, and I encourage you to take a look in the paper if you're interested. So second order, we're interested in taking this vector and dotting it with this Hessian tensor for my forward dynamics. And I'd like to do that instead by putting inverse dynamics in that place. How we do it is we construct this new quantity, mu, that is given by kind of simulating with lambda as a torque input in a sense. And we compute the following quantity. The idea here is that, this first quantity, I am using vector dotted with Hessian tensor, but now of inverse dynamics, and that's easier and cheaper to do. And I can use the same trick as on the last slide. I can reuse this information in blue from your first order dynamics. And in fact, this term in orange can be calculated using reverse mode auto accumulation as well. So the result here is that basically, we can still do this in ON squared time, and we can make use of the inverse dynamics rather than the forward dynamics, since they're more simple for us to work with. So in terms of results here, I'm showing here how this scales versus the number of degrees of freedom. Degrees of freedom on the X, time required to compute the derivatives. This is in MATLAB with Casati, so we're looking at multiple orders of magnitude slower than if you did something with in C++. But here I've got ILQR in blue and conventional DDP in maroon. So I've got this order complexity difference between them. By comparison with our new second order method for DDP, we're highly competitive with the ILQR derivative calculation times. We've also looked at how this maps onto solving the trajectory optimization problems, and the conclusion there depends a little bit on your initial guess. So for some cases, our solid blue and black are highly competitive with the ILQR in the dashed lines. If you get further, if your initial guesses are further away, then ILQR retains some benefits. But for our MPC problems that we're trying to solve, we're usually solving a neighboring optimal control problem. So I think we're going to be more kind of in this this first case. Okay, so high-level takeaways here. We've seen how DDP is applicable to hybrid systems. I've shown you this strategy with the mode sequence fixed, but timing free, where we can handle some of those switching constraints with augmented Lagrangian strategies. I hope I've given you a little bit of insight into this consideration of DDP versus ILQR. I think, you know, we've often thought that ILQR was significantly cheaper. It's still cheaper, but not as much as we used to think. And we can incorporate those second order derivatives with the same complexity as the first order. I think this has some advantages for neighboring optimal control problems, but probably less for cases without a good warm start. So with the last few minutes, I'd like to kind of think a little bit more broadly about how we should be marrying this with learning-based strategies. And I might open with you know, the question of where should we add learning? And perhaps before we do that, you know, should we add learning? And I think the answer here is a clear yes, and we've seen lots of evidence in the community that there's a lot of value that data brings to improving these strategies. But often I think we see learning as like a stand-in for good engineering, in a sense of learning is great because we don't have to have a good model to begin with. So one of the things that we've been looking at is how we can basically make it easier to do some of this model-based stuff. And so I'd like to highlight really quickly some recent work in collaboration with Tae-Yoon Lee and Frank Park. So when it comes to identifying these models, if you do kind of a conventional least squares identification of masses, center of masses, inertia terms, it's really easy to mess things up. So if you just regularize your problem using a prior CAD estimate, you can get some really bad mass distributions out of it. And so I think, you know, this is part of the reason why people like the learning strategies, is because you don't, you know, there's less to mess up. If you get if you get something wrong, you can just kind of learn it away. But we have made this much easier and much harder to mess up by introducing a new way of regularizing that is like an entropic divergence measure that has a nice connection with the KL divergence. So here these are, if I give you two inertia matrices, I can look at this divergence between them, and it's invariant to reference frames in physical units, and kind of really better encodes the natural distance between these mass distributions, and is much more forgiving and gives you much more sensible results. And so, you know, I think this is a form of learning. It's not reinforcement learning, but it's I think good engineering that we can get right so that we can learn the right things. So, you know, where should we add learning? Maybe I'll revise this. Where else should we add learning? In my mind, one of the areas that I have lots of trouble thinking about is, you know, we're working with these cost functions. If I take a picture of the environment, how do I map from world to cost function? And so in my mind, learning really is going to be entirely critical for helping us to manage the infinite complexity and of the visual information that we're bringing in. And so we've made some preliminary progress toward this with Dr. Villarreal from IIT when he was visiting my lab, where we looked at using convolutional neural nets to process vision data and decide on footholds. Footholds and gate sequences, right? Gate sequences are these things that break all of our gradient optimizers, and it's something great for our neural nets to provide for us. So we do that, and then once we have contact sequences and footholds fixed, we can do our conventional MPC strategies where we take those footholds as fixed and optimize our center of mass trajectories. And these two things can be mutually informative of one another, that better predictions for where your center of mass is going to be can inform your neural net of where it should be placing its feet. So we looked at this for a task of crossing a set of palettes with the Haiku Max. And here's a video of it. So this is only using learning to address kind of where to put the feet, when to put the feet in the gate sequence. And the rest of it is just a conventional trunk MPC. And so, I think we've seen more end-to-end type strategies do similar things recently, but in my mind, there's a great benefit here in terms of interpretability. On the outset here, we've got this model predictive controller that's thinking about forces and body position, so it makes it a lot easier for us to debug. Okay, so with that, I'll kind of wrap up here. I hope I've shown you how I think we should be thinking about our prediction in these systems. We've talked about some ways to accelerate or restructure these optimization problems and provided some very preliminary comments on choosing what to learn. I hope with these we can continue the discussion of how we can combine these MPC strategies with these learning strategies to really keep pushing our field forward. I think our community has done a really phenomenal job of that over the past 5 to 10 years, and it really shows in the results that we see coming out. I'll close by just a quick advertisement. I'm excited. We're growing our robotics footprint at Notre Dame. We've got Margaret Code coming in here in fall. She's from Stanford and worked on human-centered design and soft robots. And Edgar Bolivar, who will be joining in winter, who works on wearable and assistive robots. And we'll be complementing our strengths in controls and autonomy. And so if you're ever in our neck of the woods, we're over by Chicago, about 90 minutes east. I'd love to have you stop by and show you all that we're up to. So with that, I'll thank you very much for your kind attention and be happy to take any questions.
Okay, great. Thank you, Patrick.
Thanks a lot, Patrick.
Thanks.
Okay, Magic, do you want to ask the first question?
Yeah. So it was great, Patrick, first I should say. I have a question about, I think it was the model hierarchy. So the difference between model hierarchy or hierarchy of the MPCs that we saw. So one thing that, there are two questions actually. One is that if we do hierarchies of MPC, so we don't need to track the trajectories from the abstract model, right? We can just regularize, and this might decrease the number of iterations we need to convert to a solution from the full body MPC. This is one thing I wanted to say and ask your opinion about. And the second thing is that you said that we switch the model at the switching surface, right?
Yeah.
So if we do this, we end up having a kind of shrinking horizon or variable horizon MPC. So how do you think about that?
Yeah, that's a great comment. So that was very much a matter of convenience. You could think that you could switch models kind of at any point along the way. And I mean, being straight with you, right? It's a matter of implementation simplicity for why we made that choice. But your point is well taken that it probably, implementation wise adds more asynchronous weirdness based on the horizon kind of shrinking in time, even though it's staying fixed in terms of gate modes. And so that's a really good point in terms of as we're moving toward implementation. So yeah, I think there was another question in there.
Yeah, the first one was that if we do hierarchy of MPCs, then we can use the trajectory from simple model to regularize, or I don't know, warm start the full body MPC, and we end up having less iteration.
Yeah, well, I guess there is that question in terms of warm starting, how do you take a simple model trajectory and warm start a whole body trajectory? Because there's additional details to fill in there.
So you can do a very simple, let's say, inverse kinematics. And then you have a trajectory, and then you warm start from that. I don't think it takes so much time to do a very simple inverse kinematics on this point.
Especially if we have a centroidal model that gives you base position and you know where feet are, so you can back out legs from that. Yeah, that's a great point. I think, like you said, you would look to regularize based on the simple model, not to explicitly track based on the simple model, which is what we've done kind of often when using whole body QPs. And so I agree that would alleviate many of the challenges of using the template that we have seen in the whole body QPs. And I'm not quite sure how it would compare to ours. I guess the thing is, though, that still when you're talking about regularizing, there's always kind of this, like, a regularization strength that you have to choose. Like, how much are you pushing it toward that simplified model? And the idea that I'm saying here is that it doesn't make that much sense to push toward the simple model in the early part of the horizon, because then if your simple model is bad in any way, shape, or form, it leads you into trouble. So I think you could probably get the spirit of what we've done by taking the regularization and, like, have it somewhat loose at the early part of what you're proposing and increase it over time. And so I think you could probably get it as similar in terms of performance. Whether it would be, which one would win out, I'm not sure, but that's a neat observation.
Thanks a lot.
Okay, we have here two-part question. I asked them one by one. Did you consider using direct method instead of DDP for trajectory optimization?
Yeah, I think so. So for instance, I had mentioned that Chris Gerdes and his team, they were looking at similar ideas for planning with high-speed vehicles. And there, I think they were using direct methods with, like, IP-opt running on their high-performance vehicles. And I think, in my mind, like, the challenge with IP-opt and the other direct methods is that you can get stuck in local optima that aren't dynamically feasible. Whereas with DDP, you always have a dynamically feasible trajectory that you're working with. And so especially, online, when your time frames are quite tight, it's quite possible that IP-opt for a direct formulation would come back and it would give you an answer that, isn't a dynamically sensible trajectory. And so that's kind of been a non-starter for us in terms of thinking about the methods. But yeah, I think, the one thing is that we've often thought about DDP as being kind of special in terms of how it exploits the structure of the problem. But we've seen somewhat recently in some nice papers how, if you look at the KKTC systems associated with some of these direct problems, if you do a sparse solve, that it's actually quite similar in spirit to what DDP is doing. And so I think that the connections are closer than what we often think. But yeah, really that issue of having a dynamically sensible trajectory when stopping early has been the decider for what we've been doing versus adopting direct methods.
Okay, the second part is in your MHPC. In your MHPC work, are you able to optimize the timing for making and breaking contacts? If yes, how? Okay,
yeah. So I had talked about that briefly, but here's the idea. The idea is that let's consider a problem with a fixed time t, and what we can do is we're now going to optimize this switching time. And so what you can do is a kind of a conventional trick of doing a change of variables where you scale time. And if you do this time scaling trick, then you can rewrite your dynamics for this change of variables in this kind of revised form where you're basically speeding up or slowing down your dynamics based on how you're stretching time. And if you do that, and then you add this time as like a state in your problem, now I have a dynamic system. If I had a size n state, now I have n+1, where my time is a state variable. And I can now just throw, I have a fixed time problem, and I can throw this to DDP, and DDP will kind of, through its usual machinery, give me the sensitivity information regarding how changes in this timing variable will result in changes in cost. And so it's quite similar in spirit to actually some of the work that you did, Farbod, in terms of optimizing the switching times. But here we are getting kind of second order information by employing the machinery of DDP.
True. So the next question is, in a case of contact mode, okay, in impact aware DDP, since you have a fixed contact mode and timing, in the case of contact modes mismatch, the forward pass can't alter the contact sequence, and the new trajectory remains confined to the previous trajectory mode sequence or timing. Do you think there is a way around that within that framework?
I think that's $1 million question. Not right now. So we're fixing the mode sequence, and another area where this comes up is on in your hardware. If you assumed that your two legs were going to touch down at the same time, in reality they're going to touch down at slightly different times. And so I think the way that most people are doing it, the way that we're doing it, is with band-aid fixes in the code. And I guess the alternative there is to do something contact implicit. And I think that's something that I would like to do, that many people would like to do, but the contact implicit stuff is just so much more not ready for real time that I think it's just going to be a little while before we can incorporate those strategies. So for instance, Aaron Johnson had a nice paper somewhat recently where they were looking at a different way of doing hybrid DDP, where you would do basically a rollout on the system, and whatever mode sequence you get, that's the mode sequence that you get. And you can optimize around it to choose nearby mode sequences. But if you don't happen upon the right mode sequence with your initial guess, you're kind of hosed. And so we are fixing the mode sequence, because in my mind, if you're trotting and you should be doing something slightly different than trotting, we're probably not giving up that much by fixing trotting. Whereas for the contact implicit strategies, I think you can get yourself into a lot more trouble, at least now. But the point is well taken in terms of, like, in hardware, you're never going to have exactly the contact sequence that you assume. And I'd love to hear other folks' thoughts on how we might address that.
Indeed, as you said, this is one of the hardest challenges currently in the model-based legacy system.
Yeah.
Okay, so I have one question. So in this work that you were presenting for this ON algorithm for tensor calculation,
yeah.
Right? You have this lambda vector. This lambda vector depends on the value function, right?
It does, yes.
And then from point of view of the implementation, one advantage of this DDP-based method is that you can perform this quadratic approximation in parallel because they're independent. By now depending on the value function estimation, you're actually locking yourself to a sequential process, because you should wait until the value function reaches there, you'll be able to calculate it. So you're killing a part of your algorithm that can be parallelized. Do you have any thought how we can solve this issue?
That's a great point. So if you're going to, I agree that you can no longer compute the derivatives in parallel. However, there's lots of different, multi-shooting DDP strategies that are out there, right? Where, like, let's take for instance yours, the Gauss-Newton multi-shooting, or some of the work in your group, right? You've got this this forward pass where you are doing like a linearized forward rollout. And then during the, yeah, okay, you would probably know better than me. In that case, is everything coupled in the back pass?
No, in the back pass, you can have multiple solvers running.
You can have
multiple threads. Yeah.
Okay. And so I think in that case, right, like since the only thing that you're really worried about is propagating like information between segments from iteration to iteration, but within any iteration, you're only doing backpass on an individual segment. I think that the parallelization of this strategy would have to come through in kind of the more algorithm level parallelization. You wouldn't be able to do the super cheap thing of like, just compute all the derivatives in parallel.
Yeah, okay. So the solution will be using multiple shooting techniques here.
Yeah.
Okay, nice. Okay, Majid, you have another question, right?
No, I think I'm done.
Oh, okay.
I do.
There's another one. Sorry. Yes.
Sorry. Can I ask you a question? It's more a high-level question, but you talk at the end a little bit about learning.
Yeah.
And I asked you this question, but that's maybe a question I should ask the panel on Monday as well, because I think there's a few things we can learn. Something that I was wondering is that isn't one of the maybe the most exciting thing that we should try doing that we cannot do neither with reinforcement learning today nor with MPC is that we want robots to improve what they're doing over time.
Yeah.
I think neither our model-based approaches, which are extremely successful, nor the reinforcement learning actually techniques are capable of doing that as of today, right? How do we do that?
Well, I mean, like, I feel like we see different things being in vogue over time. So for instance, right, like in the late 80s, adaptive control was super in vogue, and that's just learning, right? It's just learning in a way that is more amenable to mathematical analysis than than what we're doing right now. And so I guess in terms of how we might be able to do that from the side of the model-based work that we're doing, I think it has to be by kind of going back to some of that literature and looking at, adaptive control now within the context of MPC, right? Because when people were doing adaptive before, it was always based on a control law where you like write down, here's my control law explicitly. Whereas now we're doing all of our control with optimization problems. And so the question in my mind, and I don't think it's an easy one, right? It's not a 2-year project. Is now that we're doing, we have these optimization-based strategies, what does it look like to do conventional adaptive control type things layered on top of them? And so I'm answering you from my more control systems bent as opposed to from a learning side, but I'd be curious. I think this would be a great thing to discuss on the panel.
Yeah, thanks. Actually, it's not so. Thanks for the answer. I think it's far from obvious what you just said. I like this. Thank you.